The following is an op-amp based adjustable current source for laser or LEDs. If R1 equal 715 ohm, R1 715 ohm, RE equal to 368 ohm, RE, RF equal to 330 ohm, RF, VI equal to 8 volts. What is current goes through the laser diode? What is current goes laser diode? We label the current and voltage in this diagram. For non-inverting pin of the op-amp, the voltage potential is V+. For inverting pin of the op-amp, the voltage potential is V-. Since there is feedback through this transistor and RF, therefore V+ equal to V-. And V+ equal to Vi, therefore V- also equal to Vi. According to the op-amp properties, I, the current through this plus pin, equal to 0. The current through minus pins also equal to 0. The current flowing through this wire equal to I0. The current flowing through this RE equal to IRE. The current flowing RF equal to I. If we assume the current goes through the RE in this direction, the voltage potential at this point is higher than the voltage potential at this point. We label here as here's plus and here's minus, means the voltage at this point is higher than the voltage at this point. We assume the current flowing through RF in this direction, so therefore the voltage potential at this point is higher than this point. So we label here as high, plus, and minus. We assume the current flowing through this R1 is in this direction, therefore the voltage potential at this point is higher than here, at this point. Now, we need to set up equations to solve the current flowing this laser diode. At this node, I0 equal IRE plus I. So I have this equation. I0 equal to I plus IRE. So I0 equal to I plus IRE. And I equal VI divided by R1. So I equal to VI divided by R1. And IRE equal to VE divided by RE. VE divided by RE equal to IRE. So I have these two expressions. Now, VE equal VI plus I times RF. VE equal to the voltage from here to here plus the voltage from here to here. So VE equal the voltage across R1 plus the voltage across RF. So VE equal to VI plus I times RF. So VI plus I times RF. And I equal VI divided by R1. We substitute this expression in here. So we have this expression. Now, we multiply 1 over RE to VI here. And then we multiply this factor in here. We have this expression. Now, we move VI out. Then we have rest 1 divided by R1, 1 divided by RE, plus Rf divided by R1 and Re. For these two terms, we make a common denominator. So as follows. Now we combine this term and this term. Finally, we got this expression. And since the base current IB is small, we assume the base current equals 0. Therefore, the current through LED or laser equal to I0. So therefore, we have I LED equal to I0. So therefore, I LED equal to VI times RE plus R1 plus RF divided by R1 times RE. This is our final expression for the current through LEDs. From this equation, we can see that the current goes through LED is proportional to the input voltage. If we increase the voltage VI, then the current goes through LED also increases. For our problem, R1 equal to 715 ohm, R equal to 368 ohm, RF equal to 330 ohm, VI equal to 8 volts. Substitute all these values into this equation, we get finally I LED equal 42.4 milliamp. Remarks: the op amp in this circuit needs only one power supply. That is, we can connect V- pin from the op amp to ground of the power supply, and V+ pin from the op amp to the VCC. And we show this in the following diagram. Here is power supply, ground, and VCC. We connect V- pin to the power supply ground, and V+ pin from op amp to VCC. Number 2, we can determine the maximum number and max of LEDs in series by the following formula. VE plus VCE. VCE is the voltage between collector and emitter of the transistor, plus and max time forward voltage of LED equal to VCC, where we leave VCE equal to 1 volt for the transistor. VF is the forward voltage of the LED. In our example, we have the following. We can calculate VE equal to VI plus VI divided by R1 times RF, which equal to 8 volts plus 8 volts divided by 750 ohm times 330 ohm, which equal 11.5 volts. VCC will take 18 volts. VF, which is forward voltage of LED, equal to 1.8 volts. We substitute all these numbers into this equation. We have the following. 11.5 volts plus 1 volt plus and max times 1.8 volts equal to 18 volts. We can find and max equal to 18 volts minus 11.5 volts minus 1 volt divided by 1.8 volts, which equal 5.5 volts divided by 1.8 volts, which equal 3.05. We take integer number of 3.05, which is equal to 3. That means in our circuit we can put 3 LEDs in series. That is maximum. We cannot take 4 LEDs in series in here. we can take one LED, two LED, and three LED in series here, but we cannot take four LEDs. Here is the Multisim results. In this simulation, we put one LED here, and R1 equals 750 ohm, RF 330 ohm, RE equal 368 ohm. VCC from power supply is 18 volts. Vin equals 8 volts. Now we observe that the voltage between inverting pin of op-amp to ground is 8.001 volts. That is V plus almost equal to V minus. And the current through LED is 41.446 milliamp. This result is close to our calculations. VE equals 11.34 volts, which is close to our calculations. Now we put two LEDs. For two LEDs, as expected, the circuit is still working. The current goes through the LEDs is 41.433. Now we put three LEDs. 3 is the maximum number of LEDs in this circuit. The current flowing through LEDs is 41.407 milliamp. Now we put 4 LEDs. From the formula we introduced before, we cannot put 4 LEDs in the circuit. Now we observe that the current goes through LEDs is 14.07 milliamp. This is not as 41 milliamp. So the circuit is normal valid.